Welcome back to Echo Mind Documentaries. If this is your first time here, make sure you subscribe to the channel. Don't forget to like, comment, and share, and turn on notifications so you never miss a story. Today's video is about a moment in history where human understanding of the universe was completely rewritten. We're stepping into a world of curiosity, imagination, and groundbreaking discovery to uncover the life and legacy of one of the greatest minds to ever live, Albert Einstein. This is not just a story, this is the reality behind the genius. A struggling student, a patent clerk with big ideas, a man whose thoughts would bend time, space, and reality itself. One theory, one mind, and a revolution that changed how we see the universe forever. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would become the most famous equation in human history. He had no academic title, he had no professor watching over his shoulder, he had only one thing: an absolute refusal to accept what everyone else had already decided was true. There is a city in southern Germany called Ulm. It sits along the banks of the Danube River, quiet and ordinary, the kind of city that history rarely notices. On the 14th of March, 1879, in a modest apartment on a cobblestone street, a child was born who would force the entire human race to rethink its understanding of reality. His name was Albert Einstein. His mother, Pauline, was a pianist who instilled in him a love of music that he would carry for his entire life. His father, Hermann, was an engineer and businessman, a gentleman full of ambition and warmth who moved the family from city to city chasing opportunity. Albert grew up surrounded by that restlessness, but even as a very young child, something about him was different. He spoke late. He thought slowly, deliberately, holding words in his mind long before releasing them. His teachers were frustrated. One of them told his parents directly that the boy would never amount to anything. He sat in classrooms staring at the ceiling, not because he was bored in the way of a distracted student, but because he was already deep inside questions that no textbook had yet attempted to answer. When Albert was 5 years old, his father handed him a compass. It was a simple gift, a small instrument in a brass case, its needle trembling and pointing north no matter which way it was turned. Most children would have played with it for an afternoon and set it aside. Albert could not let it go. He stared at it for hours. Something he knew was pushing that needle, something invisible, something he could not see or touch or explain. That moment, that trembling needle, planted the seed of a curiosity that would define every year of his life. By 10, he was reading philosophy. By 12, he had taught himself calculus. He moved through the world of ideas the way other boys moved through fields, running freely, without fences. His family relocated to Munich, then to Milan, then to Zurich. Each move uprooted him. Each city added a new layer to the restless, searching quality of his mind. He applied to the Swiss Federal Polytechnic School in Zurich at 15, 2 years younger than most applicants. He failed the entrance examination. His French and botany scores dragged him down. He spent a year in the small Swiss town of Aarau, attending a school whose philosophy emphasized visual thinking and independent reasoning. It was, for Einstein, a revelation. For the first time in a formal classroom, he felt genuinely free to think. He reapplied to Zurich, passed, and enrolled, but his relationship with formal education remained complicated. He skipped lectures, he argued with professors, he trusted his own instincts over assigned readings. A fellow student named Marcel Grossmann took meticulous notes and shared them with him before exams. Without Grossmann, Einstein might never have graduated. He graduated in 1900 with a teaching diploma, but no university would hire him. He applied to position after position and received nothing but silence in return. Hermann Minkowski, one of his professors at Zurich, once called him a lazy dog. The irony is almost too large to contain. The man who would redefine the nature of time itself could not get a job teaching physics to teenagers. It was Grossman, once again, who saved him. Grossman's father knew the director of the Swiss patent office in Bern. Einstein was offered a position as a technical expert, third class, reviewing patent applications submitted by inventors. It paid a modest salary. It required him to sit at a desk for 8 hours a day and examine mechanical and electrical inventions for logical consistency. He was extraordinary at it. He worked so efficiently that he finished his official duties in a fraction of the time allotted. And in the hours that remained, quietly at that same desk, in that same small office, he thought about the universe. He thought about light. He had been thinking about light since he was 16 years old, when he first posed a question to himself that no physicist had quite asked in the same way. What would a beam of light look like if you could ride alongside it at the same speed? Classical mechanics, following Newton, suggested that the light would appear to stand still, like a river seen from a boat moving at the same current. But Maxwell's equations describing electromagnetic waves said something entirely different. They said light always travels at the same speed, regardless of the observer. These two frameworks, Newton's mechanics and Maxwell's electromagnetism, could not both be right. Every physicist in the world knew the contradiction existed. Most assumed it would be resolved with more data, better instruments, a refinement of the existing theories. Einstein alone sat with the discomfort long enough to realize that the resolution required something far more radical. It required throwing away an assumption so fundamental that no one had thought to question it: the assumption that time is fixed. The assumption that a second lasts the same length everywhere in the universe for everyone, always, without exception. What if it did not? In the spring of 1905, Albert Einstein was 26 years old. He was still a patent clerk. He had a wife, Mileva, a Serbian mathematician he had fallen in love with at Zurich, and a baby son named Hans Albert. He lived in a modest apartment. He had no laboratory, he had no grant, he had no colleagues reviewing his work. He had a mind, a stubborn willingness to follow a thought wherever it led, and a deep, almost spiritual conviction that nature at its core is elegant and consistent. Between March and September of that year, Einstein published 4 papers in the journal Annalen der Physik. 4 papers in 8 months. Any single one of them would have been enough to secure his place in history. The first explained a photoelectric effect, demonstrating that light is not only a wave, but also a particle, a quantum of energy he called a photon. This paper would eventually win him the Nobel Prize. It was the paper that helped give birth to quantum mechanics, the science of the very small, the framework that now underlies every semiconductor, every computer, every smartphone on Earth. The second provided a mathematical explanation for Brownian motion, the random zigzagging of particles suspended in a fluid, and in doing so offered the first definitive indirect proof that atoms actually exist. This was not a trivial matter. In 1905, many scientists still disputed the physical reality of atoms. Einstein settled the argument with mathematics. The third paper was the special theory of relativity. It began with 2 simple postulates. First, that the laws of physics are the same for all observers moving at constant velocity relative to one another. Second, that the speed of light in a vacuum is constant for all observers regardless of the motion of the light source or the observer. From these 2 premises, working through pure logic, Einstein derived consequences that staggered the mind. Time dilates, moving clocks run slower, length contracts in the direction of motion. Simultaneity is not absolute. 2 events that appear simultaneous to one observer may not appear simultaneous to another. The universe is not a stage with a fixed background of space and time upon which events play out. Space and time are woven together into a single fabric, and that fabric behaves differently depending on how you move through it. The fourth paper, arriving a few months after the third, contained a short but shattering addendum to his relativity work.
a 3-page derivation that ended with an equation so compact it seems almost impossible that it could mean what it means. Energy equals mass times the speed of light squared. E equals mc squared. In 9 characters, Einstein revealed that matter and energy are the same thing, interchangeable, with the speed of light squared acting as the conversion factor between them. The amount of energy locked inside even a tiny amount of mass is almost beyond human comprehension. A single kilogram of matter fully converted to energy would release an explosion equivalent to roughly 21 megatons of TNT. The physics world took time to notice. The papers circulated. A few senior scientists read them carefully. Max Planck, one of the most respected physicists in Europe, recognized immediately that something extraordinary had happened. He began citing Einstein's work. Invitations began to arrive. Slowly, then rapidly, the name Albert Einstein moved from obscurity to the center of theoretical physics. By 1909, he had his first academic position, a professorship at the University of Zurich. By 1913, he was in Berlin at the Prussian Academy of Sciences, the most prestigious scientific body in the world, with no teaching duties and complete freedom to think. He was 34 years old. And he was already deep into the next problem. The special theory of relativity described physics for observers moving at constant velocity. But what about acceleration? What about gravity? Newton's law of gravitation described how gravity behaves mathematically with extraordinary precision. But Newton himself admitted he had no idea what gravity actually was, what mechanism caused objects across vast distances to pull toward one another. He called it action at a distance and left it as a mystery. Einstein could not leave it as a mystery. He began with what he called his happiest thought. A man falling freely in a vacuum would feel no weight. Gravity would be completely undetectable to him. This was not just an observation. Einstein recognized it as a deep clue about the nature of gravity itself. A gravitational field and an accelerating reference frame are locally indistinguishable. This is the equivalence principle, and it became the conceptual cornerstone of everything that followed. For 10 years he worked on it. He filled notebooks with equations and abandoned them. He reached dead ends, doubled back, started again. He collaborated with Grossman, now a mathematician, who taught him the advanced mathematics of curved geometry developed by Riemann in the 19th century. The mathematics was brutally difficult. Einstein, who had always trusted physical intuition over pure calculation, now had to submit himself to years of grinding mathematical discipline. There were periods when he believed he had found the answer, only to discover a fatal flaw days later. There were times he was certain the project was impossible.
In November 1915, he stood before the Prussian Academy of Sciences in Berlin and presented the General Theory of Relativity in 4 consecutive weekly lectures. What he presented was nothing less than a completely new theory of gravity. In Einstein's framework, gravity is not a force in the Newtonian sense. It is the curvature of space-time caused by the presence of mass and energy. A massive object like the sun warps the fabric of space-time around it, the way a heavy ball placed on a stretched sheet of rubber creates a depression. Other objects, including light, follow the curves of that warped space-time. What we experience as the pull of gravity is actually the natural motion of objects following the geometry of curved space-time. The mathematics produced a set of field equations of extraordinary elegance and complexity. They described the geometry of the entire universe. They made specific, testable predictions that differed from Newton's predictions in precise ways. One of the most dramatic was the prediction that the path of light should be bent by gravity, not just slightly, by a specific calculable amount. 4 years later, on the 29th of May 1919, a total solar eclipse swept across the Atlantic and Africa. 2 British expeditions, one led by Arthur Stanley Eddington in the island of Principe off the west coast of Africa, the other in Sobral in Brazil, photographed stars visible near the edge of the eclipsed sun. The positions of those stars were compared to their known positions when the sun was not between them and the Earth. If Einstein was right,
The stars should appear shifted from their true positions because the sun's gravity was bending the light passing near it. The measurements, when analyzed and announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London on the 6th of November 1919, confirmed Einstein's prediction to within the margin of experimental error. The Times of London ran the headline the next morning: "Revolution in Science, New Theory of the Universe, Newton's Ideas Overthrown." Overnight, Albert Einstein became the most famous scientist who had ever lived. Fame is a strange companion for a man who thinks in silence. Einstein handled it with a mixture of delight and weariness. He was charming and witty in public, a master of the quotable phrase, generous with his time for causes he believed in. But inside, he was already wrestling with the next layer of the problem, trying to do something that physicists are still attempting today. He wanted to unify all the forces of nature into a single coherent framework. He wanted one theory that explained everything. He never succeeded. He would spend the last 30 years of his life on this pursuit and arrive at the end without the answer. Many of his contemporaries believed he had lost his way, that his insistence on determinism and elegant mathematics had led him away from the probabilistic reality that quantum mechanics was revealing. He and Niels Bohr, the Danish physicist who was central to the development of quantum theory, engaged in one of the most consequential scientific debates of the 20th century. Einstein famously insisted that God does not play dice with the universe. Bohr replied with equal firmness that it is not for Einstein to tell God what to do. History has been more complicated than a simple winner and loser. Quantum mechanics works. Its predictions have been verified with astonishing precision. But the puzzles Einstein raised about it, the questions about whether its description of reality is truly complete, remain genuinely open. The philosophical argument he started with Bohr is still very much alive in physics today. The 1930s brought catastrophe to his personal world. He had been born in Germany. He had built his career in Germany. But the Germany he returned to after the eclipse confirmation was changing in ways that would soon make it uninhabitable for him. He was Jewish in a country moving rapidly towards a virulent, murderous anti-Semitism. The Nazis attacked his physics, calling it Jewish science, a propaganda category designed to discredit whatever they wanted to dismiss. When Adolf Hitler became Chancellor of Germany in January 1933, Einstein was visiting the United States. He never returned. He resigned his membership in the Prussian Academy. He found a permanent home at the newly founded Institute for Advanced Study in Princeton, New Jersey. In August 1939, deeply troubled by reports that German physicists were exploring the possibility of a nuclear chain reaction and what it might mean in the hands of the Nazi government, Einstein signed a letter to President Franklin D. Roosevelt. The letter, drafted primarily by physicist Szilard and co-signed by Einstein, warned that it might be possible to set up a nuclear chain reaction in a large mass of uranium, and that this phenomenon would lead to the construction of bombs of a new type with enormous destructive power. That letter contributed to the chain of events that became the Manhattan Project. And the Manhattan Project produced the bombs dropped on Hiroshima and Nagasaki in August 1945. Einstein was not involved in the Manhattan Project. His security clearance was denied. Military intelligence considered him a potential security risk because of his pacifist and socialist associations. But his equation, E equals mc squared, was the theoretical foundation upon which the entire enterprise rested. When he learned of the bombing of Hiroshima, he said only, "Oh vey," the French phrase for "oh no." The weight of it never left.
In the years after the war, he threw himself into causes. He was a committed pacifist and internationalist, a believer in world government as the only rational response to the existence of nuclear weapons. He campaigned against McCarthyism, against racial segregation in America, against the arms race that was already accelerating between the United States and the Soviet Union. He was watched by the FBI for years. J. Edgar Hoover maintained a file on him that grew to nearly 1,400 pages. He worked at Princeton in a simple office. He walked to campus. He played his violin. He received visitors, answered letters from students and strangers, sat for photographs with a patience born of long practice. The wild white hair had become an icon, the image the world reached for when it needed to picture what a genius looks like. He wore the image lightly, with humor, and continued every morning to sit down with his mathematics and reach for what remained beyond his grasp. On April 17, 1955, Einstein was admitted to Princeton Hospital with severe abdominal pain caused by the rupture of an aortic aneurysm. He was 76 years old. A surgeon urged immediate operation. Einstein refused. He said, "I want to go when I want. It is tasteless to prolong life artificially. I have done my share. It is time to go. I will do it elegantly." He died in the early hours of April 18, 1955. At his bedside were several pages of mathematical equations, his final attempt at a unified field theory, still unfinished, still reaching. His brain was removed by the pathologist Thomas Harvey during the autopsy without the consent of his family and preserved for scientific study. It has been examined by researchers for decades. Some studies have found unusual features in the parietal lobes and the density of glial cells. None have explained what he was or how he saw what he saw. What is the legacy of Albert Einstein? It is both finite and boundless, depending on where you look. In the finite register, the list of technologies that trace back to his work is extraordinary. GPS satellites must account for the relativistic effects he predicted, or they would accumulate errors of miles per day. Lasers, the foundation of everything from barcode scanners to fiber optic communication to surgical instruments, are built on the stimulated emission of radiation that he first described in 1917. The microchip industry, the entire digital world, rests on quantum mechanics, which his 1905 photon paper helped initiate. MRI machines use principles that flow from his work. Nuclear power, for better or worse, follows from E equals mc squared. In the boundless register, the legacy is something harder to measure and perhaps more important. He demonstrated what a single human mind, freed from the obligation to agree, is capable of achieving. He showed that the deepest truths about the universe are accessible not to those with the most equipment or the most credentials, but to those with the most relentless honesty about what they do not yet understand. He failed. He failed his entrance exam. He failed to get an academic job. He failed to stay married to Mileva. He failed to find the unified field theory. He failed to accept quantum mechanics on its own terms and spent decades in a productive but losing argument with the direction physics was moving. His life was not a clean arc of triumph. It was a human life, full of loss and longing and stubbornness and error. What set it apart was not the absence of failure, but the quality of the questions he refused to stop asking. The universe is approximately 13.8 billion years old. It contains somewhere between 200 billion and 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. The physical laws that govern every particle in every star in every galaxy across all of that incomprehensible distance and time are the same laws that a young man sitting at a patent clerk's desk in Bern, Switzerland in 1905 glimpsed through the window of his own imagination. Albert Einstein did not change science. He changed what science could see. He moved the horizon. He handed the human race a new pair of eyes and said, "Look again. Look harder. Look honestly. The universe is stranger and more beautiful than you have yet allowed yourself to believe." And it is. Because of him, it always will be.